In this video, we present our recent work on bridging the synthetic-to-real gap, titled Attribute Subspace Mining for Robust 3D Model Adaptation. A recent trend in adapting 3D foundation models is supervising them with monocular priors. These methods use monocular depth or geometry estimators as teachers to guide 3D foundation models during fine-tuning. However, they still rely heavily on 2D visual cues. They transfer monocular priors into 3D representations, but do not explicitly model the intrinsic physical factors of the 3D world. Our motivation is different. Instead of using monocular teachers, we ask whether the 3D world itself contains disentangled attributes, such as texture, geometry, camera, and lighting, that can be directly mined for robust model adaptation. Our key question is, how can models extract real-world transferable features from synthetic data? Although synthetic and real images may have a large appearance gap, they can still share the same underlying 3D attributes. Our solution is to mine attribute subspaces from synthetic data. These subspaces capture transferable 3D variations and provide a compact space for robust model adaptation. Here is an overview of our framework. First, we construct synthetic datasets with controlled attribute variations, including texture, geometry, camera motion, and lighting. Then, for each type of variation, we fine-tune LoRa adapters and extract the corresponding attribute subspaces. Finally, we integrate these subspaces into a compact LoRa basis for downstream task fine-tuning. In this way, the model can adapt to real-world tasks efficiently, even when the subspaces are mined entirely from synthetic data. Our first downstream task is 2D face anti-spoofing under the microbaseline setting. Here, both the subspace extraction data and the fine-tuning data contain no face semantics. They are purely synthetic scenes. However, they share important 3D attribute distributions with the target task, especially the microbaseline camera motion. This allows us to test a key question. Can semantic irrelevant synthetic data still improve a real downstream task as long as the underlying 3D attributes are shared? The results show that all fine-tuning methods improve over the original VGGT model, indicating that these shared 3D attributes are indeed useful. More importantly, our subspace-based method achieves better reconstruction quality with fewer trainable parameters and fewer artifacts. This demonstrates that the extracted attribute subspaces are more effective and more transferable than standard fine-tuning strategies. We further evaluate our method on clothed human reconstruction to test cross-domain generalization. Here, the target data are real human scans, which are very different from the synthetic data used for subspace mining. Even under this large domain gap, our method achieves strong performance. This shows that the extracted attribute subspaces are transferable and can generalize beyond the synthetic domain to real-world reconstruction tasks. Transparent object reconstruction is a highly challenging setting with limited training samples and complex refraction and reflection effects. Importantly, we do not introduce any sampling of transparent textures when mining the subspaces. Even under this difficult and data-scarce setting, our method still transfers effectively and achieves competitive performance. This further demonstrates the robustness and transferability of the learned attribute subspaces. We hope our findings provide a new perspective for understanding and adapting 3D foundation models. Thank you very much for your attention.